So today we're going to be talking about optimization. This is a new unit. I'm just going to do a couple of days of this just to give you a sense of what types of problems you'll see in calculus. Optimization is one of the most common applications in calculus. We often hear terms like least time, greatest profit, shortest distance, maximum volume, minimum waste, etc. In order to optimize problems of this sort, we first need to find the quantity that needs to be minimized or maximized. We're going to do the same thing regardless. Be sure to assign variables, write a function that represents the minimum or max needed, and to find the minimum or maximum values, we're going to use the key concept that a minimum or maximum occurs when the derivative is zero. Okay, so before we really start, I just want to show you the connection to curve analysis. Okay, so we have this curve f of x. We've already talked about the fact that our curve can have what we call relative maximum and relative minimum values. Well, how does the derivative come into play? Well, we know these relative minimum and maximum values occur when we have a tangent line, a horizontal tangent line. In other words, the slope is zero. Well, how do we figure out where this occurs? We find that by setting the derivative equal to zero. So ultimately, that's what we're going to do in each of these problems. While no two problems are the same, having a strategy or method helps us. So here's a huge list of information. It looks like a lot of words. I sort of highlighted the important parts. And I just want to point out to you that the first 4 steps we already went over in the beginning of the year. And the last steps are what's going to connect the calculus to this topic. So basically, when we were in our functions unit and we had to create a function, we always drew a picture. Then we assign variables to all the given quantities and any quantities that need to be determined. We then write a primary equation. Okay, so ultimately, we're going to decide what needs to be minimized or maximized using usually one of these. Okay, I'm not going to go through them all right now because we're just going to use what's specific to the problems we're going to be working with. After that, we find a secondary equation that connects our variables together. Okay? And after that, we can write a primary equation in terms of a single variable. And if you remember, we did that in our functions unit earlier in the year. After we have that all set, you find the derivative. You set the derivative equal to 0. And then you plug back in to find the values that are being asked for. Be sure to answer the questions fully. Okay, so just be aware, we're going to try to focus on that as we move through problems. If they don't give you instructions on rounding, always round 3 places. All right, so you might want to keep this paper near you, next to you while we're working through problems because it will be very helpful. So we're going to start with our first problem. The size of a bacteria population found in some food grows at a rate of P of t equals 8,000 t over 80 plus t squared, and t is measured in weeks. Determine when the bacteria will reach its maximum size and what is the maximum size. So we have a when and a what. So the when is going to be the t we solve for, and the what is going to be what we get when we plug back into the original. Okay, so we're going to look here. This really, we can't draw a picture of it. I'm not going to try to draw bacteria. So we look and they give us, this one's nice because they give us our function and it's all ready to go. So what I would need to do is I need to find the derivative of this function. Had it not been all ready to go, I would have had to create a function. So I'm going to start by finding the derivative of this function. Bottom, derivative up the top. Now you could probably work through this on your own. You don't need me anymore. Top, derivative of the bottom, over the bottom squared. And don't get upset if you think these numbers are large and crazy. You get to use your calculator. I'm going to just work through and simplify this guy. I'm not going to really describe what's going on here because I expect you to know this math by now. 0, sorry. 80 plus t squared squared. Now that I have a derivative to work from, I can take this derivative, set it equal to 0. We don't really care about the undefined part of this. We only care about it being equal to 0. So if I set the derivative equal to 0, I'm just setting the numerator equal to 0. And I wind up getting t squared equals 80. Okay, so I have my t squared equals 80. So t is going to equal plus or minus 8.944. And now here's a great thing to talk about, okay? So I have two answers here. Which one is the maximum? Which one is the minimum? Well, here, since we're dealing with, instead of getting a number line and testing and doing all that nonsense, use some common sense. We're dealing with time, so we have to take the positive value. So the when part of this is when t equals 8.944 weeks. And now we want to find the what. And we're going to get the what by plugging t back into the original, because that gives us the population. So when I plug t into the original, you're going to have your calculator, so you'd work through that math, and you wind up getting 447.214 bacteria. Okay. So that one was a really easy example and straightforward, because the function you were taking the derivative of was already there for you. In the next couple of examples, we're going to have to come up with the functions. So now they're going to become a little bit more challenging. In example number 2, find two positive numbers such that the sum of the first and twice the second is 64, and whose product is a maximum. So I would first kind of start here. I'm trying to maximize the product. This is going to be my equation. This is what I'm going to take the derivative of. So if I'm maximizing the product, I'm maximizing the product of two numbers. So one number is x, one number is y. Now I need to get this all in terms of x's. So I go back up into my problem, and I use the other information there to help me out. Find two positive numbers such that the sum of the first and twice the second is 64. So sum means to add. So I have x, that's my first number, twice the second, 2y, equals 64. Now what I want to do is I want to write this all in terms of x's or y's. It doesn't matter. So I'm going to say I'll solve this. I'm going to actually write it in terms of y's, because to solve for x is easier. I go back over here. P equals x. I'm going to replace x with 64 minus 2y times y. Distribute this out, make it nice and pretty for yourself. So we have 64y minus 2y squared. Now I have a function. It's all in the same variable, so here's where I'm going to start with the second part of the process. Take the derivative, set it equal to 0, and solve. P prime is going to equal 64 minus 4y. So 64 is equal to 4y, and we get that y is equal to 4. So I have one of my numbers. I need to find the other number, so I need to find my x value. So x equals 64 minus 2 times y, which is 4. X equals 64 minus 32. So x equals 32. So your answers here, x equals 32, y equals 4. Okay. So that's going to be two positive numbers that the sum of the first and twice the second is 64. Okay, and the product of those two numbers is the maximum. You could go back in if you wanted to and check it out, but I'd rather just move on to the next example. Example number 3. A rectangle has its two lower corners on the x-axis and its two upper corners on the curve y equals 16 minus x squared. Find the dimensions, so I need the length and the width, of the rectangle with the largest area. Now, to set up this problem, here's where things might start to seem familiar to the beginning of the year. If I look at this curve, y equals 16 minus x squared, this is an upside down parabola. Right, here's my curve, y equals 16 minus x squared. And you know, I would usually give this picture to you, so don't be so afraid of the picture. So it's two lower corners on the x-axis. It's two upper corners on the curve. And we would probably be given a picture that looks like that. And we want to find the dimensions, right? This is going to be a point on the curve. We want to find the length and the width of this rectangle that's going to give us the largest area. So what do I want to find? I want to find maximum area. So the first place I begin is creating my primary equation. I want to maximize area, so I go back to what I know, area is length times width. Now I need to connect the information together, so I can write this in terms of one variable. Go back over to my picture, and we know, again, from earlier in the year, the length of this rectangle is going to be x and x. So my length is 2x. The width of this rectangle is y. So I can start making my substitutions. Length is 2x, width is y. Now I want to get this equation with all x's. So I need to make a substitution. Well, I know that y equals 16 minus x squared, so I can replace y with 16 minus x squared. Now I have an area function. I just need to kind of distribute so I can take the derivative. 32x minus 2x cubed. There's my derivative function. There's my function. Take the derivative, set it equal to 0, and solve for x. 32 minus 6x squared, set it equal to 0, and I'm going to solve this guy. I get 6x squared equals 32. Oh, this is not going to be so nice. X squared equals 32 over 6. Take the square root, and you would get x equals, I'm just going to change this into a decimal. So obviously here, what we found was the positive value of x and the negative value of x, 2.309. Okay, so we're just going to work with the positive, again, because we're dealing with area and distance. That's our x value. Now we have to be careful, because what we really want for our answer are the dimensions. And dimensions are length and width. So we have to decide how we're going to get our length and our width. Well, go back over here. Our length is really 2 times x. So we're going to substitute that guy in. The length of that rectangle would be 4.618. And our width is 16 minus 2.309 squared. So our width with a little help from our calculator, would be 10.669. Okay. We don't need to write any units on this because we weren't given units in the problem, so we're all set with this guy. We're going to do one more example together. I included some homework questions on this, but these completely optional. I just put them on there in case anybody, wanted to do more. Let's look at the last example together and we'll be done. Ooh, this one's a doozy. At what point on the graph of y equals negative 3x plus 5 is closest to the point negative 1, 0? Okay, so closest, I'm minimizing. And let's take a look at the picture before we decide how to move on. And I should have included pictures, but I didn't. 2, 3, 4, 5. So I'm just sketching the line y equals negative 3x plus 5. Y-intercept of 5, slope of negative 3, in a really not very careful way. I'm just sketching that line. Again, the picture is just really a visual aid. And I want to know what point on this line is going to be closest to that point. So if we want, and my picture's not very good, but if we wanted to find the point, right? What are we going to be using? Right? To help us find the point, we're going to have to set up the distance formula. Okay? So when we were going to minimize distance. I'm going to start with my distance formula like I was taught in geometry. x2 minus x1 squared, y2 minus y1 squared. And now I'm going to substitute values from my picture. And I hope all of you remember back to the beginning of the year when we did this. x2 minus x1. y2 minus y1. And now we have to clean this up and get it in terms of one variable. X plus 1 squared, and y is negative 3x plus 5 minus 0, so this is just going to be negative 3x plus 5 squared. This gets multiplied out and cleaned up. Distance equals x squared plus 2x plus 1 plus 9x squared minus 30x plus 25. I'm going to combine my like terms. 10x squared minus 28x plus 26. Unfortunately, we still have to take the derivative. So when I have something under a square root sign, in order to take the derivative, I have to rewrite it with a power. This guy here is a chain rule. So d prime becomes 1/2 derivative of the outside. I'm going to leave my parentheses, whatever's in here alone, times the derivative of the inside. 20x minus 28. And I'm going to run out of room. Okay. So now I'm going to rewrite this so I could see what I'm dealing with. D prime equals 20x minus 28 over 2. So that becomes 10x minus 14. And this whole thing is going to go on the bottom. And remember, I'm setting this equal to 0. I don't care about the denominator. All I care about is the numerator. So x is going to equal 14 over 10, or 7/5. So the x coordinate, think about it. that's closest is on the line is going to be 7/5. How am I going to get the y value of that point? Well, I'm just going to plug it into the equation. So I have y is going to equal, this is negative 21/5 plus 5, and I get negative 21 plus 25 is 4/5. So the actual point on the curve that's closest to the point negative 1, 0 is the ordered pair 7/5, 4/5. Okay. So I just, want to spend this time at this point in the year just to kind of try to connect some of the things we did in the beginning of the year with now the topics we've been studying, to show you where this stuff is going to be leading you in the future. Feel free to try any of the homework questions on your own, but there's no reason to. I just want you to be able to work through the things with me each day in class together. So long.